I am Jack Funk, Chief of Flight Test at Boeing, Wichita. The picture you're about to see is a simple compilation of footage, hastily put together from the flight test strips available in the Boeing Film Library. Yet we believe the story it tells is as important as any in recent aviation history. Our film spans 10 years of time. It commences with our first attempts to comprehend the low-level environment into which we were suddenly projected in the mid-1950s. It continues to the recent near loss of a B-52 test airplane and the follow-on Gust investigation with an instrumented F-106. Some of our early work preceded other investigators and in a sense is still unique. Our flight test centers have covered the many facets of low-level operation, from an attempt to better understand the natural phenomenon to the structural aspects, to equipment development, to the human factors involved with operating high-performance aircraft below enemy radar detection. In looking back across these past 10 years, it occurs to me that our greatest and most recurrent problems have stemmed from an inadequate knowledge of the turbulence associated with the low-level operation. During 1954, and in conjunction with the B-47 low-altitude toss bombing program, our test airplane was fitted with a gust boom and operated for a brief period of time in the Wichita Mountains near Fort Sill, Oklahoma. The objective of this program was to determine the true velocity of a discrete gust and correlate it with aircraft structural loads. One other interesting aspect of the program was the correlation between measured meteorological data and the gust phenomena as obtained by the aircraft. This short program was limited to a seasonal period in which the maximum gust velocities did not exceed 30 to 35 feet per second. In retrospect, it is unfortunate that the time of year and geographical locations were not characteristic of the operations required today. Cameras mounted atop the vertical fin and in the fuselage looking along the wing leading edge show the aircraft structural response to discrete gust encounters. An over-the-shoulder camera records activity of the panel accelerometer. Airplane roll and yaw motion is noticeable, particularly from the forward viewing cameras. The highest velocity gusts were obtained by flying the aircraft through saddlebacks and the ridge lines. The data accuracy of this program was limited in that the instrumentation system and manual data reduction program did not permit adequate time integrations or calibrations necessary to precisely determine the true Earth reference gust velocities. Consequently, only the onset or initial portion of each strike could be used to evaluate its shape and velocity. Additional B-47 boom work, similar to the B-66 program, was accomplished in 1959. Even though considerable data were obtained on these projects, there remained questionable areas in completely understanding the airplane motion and boom dynamic contributions to the measured gusts. Recognition of the limitations surrounding these earlier programs and the comprehensive operational experience gained by the Wichita flight crews and test engineers have provided an analytical insight to the complex problems associated with this type of flight test work. These same experiences have also added to our concern for operating aircraft in this new environment. In the late 50s, the tactical attention was shifted from the constant altitude low-level operations to a more difficult mission which required terrain contour following at drastically reduced altitudes. A great deal of emphasis was placed on the development of systems to allow the crews to perform this type of mission. Boeing Wichita pioneered in this field, adapting the low-level advanced capability radar system to the high-altitude B-52. With the increased amount of systems test work over all types of terrain and throughout all 4 seasons, it became very apparent that we needed to know much more about the severity and characteristics of low-level turbulence. As the result of a loss of a B-52 at Burns, Oregon, all of our test inventory aircraft were equipped with cockpit displays such as sensitive accelerometers, stress indicators, and airplane side slip instrumentation. This was done to provide our test crews with some means of evaluating the severity of turbulence. In the intervening years from the B-47 to the B-52, many important advances in data recording and reduction methods had taken place. Our systems progressed from the photo boxes and oscillographs with the attendant manual data reduction in the early days to the magnetic recorders and electronic computers of today. We are presently using narrowband FM and high-fidelity PDM recording media with playback and strip-out capability in our specialized ground station. The final data treatment is accomplished on 1401 and 7094 equipment. data cycle time has been reduced to a minimum. As we've gained more knowledge of the load transfer functions and the dynamic ratios of our structural system, our interest in correlating the derived gust with absolute gust velocities has increased. We now feel, with a high degree of confidence, that such correlation can be accurately performed with modern instrumentation. Recent advances in miniaturization of instrumentation will now allow the required sensors to be installed in the gust boom itself. It is reasoned if time histories of rate and direction of motion are finitely measured, simultaneous with differential and total pressure measurements, then the aircraft and boom dynamics can be accurately and completely removed from the determination of true Earth reference gust velocity. We are currently pursuing the design of such a system. The progress to this point is very encouraging. For instance, a 3-axis gyro platform capable of being fitted into the boom is now undergoing qualification tests at our facility. In addition, we will install sub-miniature rate gyros and accelerometers in the tip of the boom. A possibility also exists for hot wire anemometers located adjacent to the pressure probes. Caging and zeroing devices will be employed to provide periodic calibration and minimize instrumentation drift error. The entire assemblies, including recording media, will be mated, tested, and calibrated in the wind tunnel before installation on the aircraft. Response to dynamic conditions will also be ascertained in the tunnel before flight. It is believed considerable advancement in the science of gust boom measurement will result. 2 of our B-52s, an early and a late model, which are already instrumented to measure loads, will receive these gust boom systems during the 1128 structural modifications this fall. After these aircraft are returned to flight status, it will be possible to correlate measured true gusts with the aircraft structural response and thus validate or refine the theoretical load transfer functions. These boom systems will also allow us to better define the physical shapes of the gust as they exist in nature. In addition, many side benefits will accrue in that the test vehicle so equipped will be in a position to determine, in a limited manner, the seasonal trends, to survey the B-52 operational routes, and to evaluate equipment intended to detect turbulence. One important point should be made in reviewing the scope and scheduling of these B-52 boom programs. Because of committed flutter investigations and structural demonstrations, the first aircraft will not be available to conduct environmental testing until the end of the first quarter of calendar 1965. By that time, the opportunity to test during the more severe winter season will have been lost. We would strongly recommend that someone instrument additional aircraft and commence a turbulence test program before 1 January next year. These aircraft, if selected immediately, could be equipped in sufficient time to conduct an environmental research program starting with the more severe weather time period. The test should encompass all seasons to detect cyclic trends and should correlate topography and meteorological data with the severity of turbulence. The aircraft which you will soon see sans vertical stabilizer is one of our test airplanes. The purpose of its flight on 10 January 1964 was to measure in-flight loads during a low-level operation. The flight, as it turned out, was very dramatic, to say the least. The low-level portion of the mission was conducted on Boeing Route Number 2. This route had been selected to represent a cross-section of all terrain types expected to be encountered in the continental United States. It varied from flat terrain in western Kansas to foothills and rugged mountains in Colorado. The mission was a 500-foot contour operation. The weather was briefed to be high broken clouds, winds from the south at 15. Moderate clear air turbulence was forecast for high altitude. There was no forecast turbulence at the low levels. At Wagon Mountain, New Mexico, the aircraft turned and began its northbound course parallel to and east of the Sangre de Cristo mountain range. Turbulence began to increase from light to moderate as the flight progressed. The frequency of encounter of moderate turbulence forced the crew to climb into smoother air before conducting the next 10-minute condition. The turbulent level remained approximately the same as at the lower altitudes until the aircraft passed through 14,000 feet. At this altitude, the turbulence subsided and the aircraft was leveled and accelerated to 350 knots. Doppler winds had been steadily increasing. Shortly before the encounter, the winds were recorded at 62 knots. As the aircraft passed adjacent to East Spanish Peak, elevation 12,700, extreme turbulence of a very short duration, 9 seconds, was experienced. Throttles were immediately reduced to idle and the aircraft rapidly decelerated. The pilot alerted the crew to prepare to abandon since he suspected severe structural damage. He was able to regain lateral directional control by trading off the yaw and roll response of the spoilers. It was not possible to physically observe the damage. However, by analyzing the control requirements, the pilot did determine that the aircraft still had a small margin of directional stability, which could be augmented by extension of the aft gear and outboard air brakes. A SAC B-52 working at low level in the area provided turbulence reconnaissance and advised a descent to lower altitude east of the mountains. The aircraft was later intercepted by an F-100 out of Wichita, and first confirmation of damage was given the crew. The vertical stabilizer and rudder had been sheared from the aircraft, leaving only a short, ragged fin base attached to the fuselage. In addition, the right elevator and structural bulkhead, which attaches the vertical and horizontal stabilizers, had sustained major damage. It was elected to recover the aircraft at Blytheville, Arkansas, because of the unfavorable surface winds, turbulence, and populated approaches at Wichita. A flaps-up landing configuration was determined to be the best because of the higher margin of stability at the elevated approach and touchdown speeds. The landing was accomplished without further incident or damage 5 hours after the strike. From the instrumentation on the airplane, the lateral gust which sheared the vertical surface was calculated to have an equivalent velocity of approximately 100 feet per second. At the density altitude of the strike, the true velocity is equated to approximately 120 feet per second. In the weeks that followed, it was determined that a more suitable airplane equipped with Gust probe instrumentation should be sent into the area to accumulate additional data on this type phenomena. ASD had an F-106 equipped with a nose boom and an narrowband FM recording system designed and used for past programs. This airplane was pressed into service and during the months of March and April staged out of Kirkland Air Force Base. An F-100 airplane was used for reconnaissance and escort pacer. During the 7 weeks, a total of 61 test flights were accomplished and over 90 hours of data were recorded. Boeing supported the program with test engineers, instrumentation engineers, and airplane maintenance personnel. We were fortunate that the instrumented F-106 was available for this program. We were fortunate, too, that we had had some prior experience with this particular airplane and instrumentation. It had been used in conjunction with an earlier B-52 test program. As a result of this experience, the problems in recovering the data from the F-106 magnetic tape using our previously written computer programs had been largely resolved. Conditions were just right for a quickie test, with a chance to look at some immediate results. Data tapes were returned to Wichita for processing via commercial air on a day-to-day basis. Even though it was anticipated that this test would produce significant and unique results, it exceeded all of our expectations. The data yield is most informative, both in magnitude and frequency of gust encounter. These low-level scenes were obtained from a gun camera installed on the F-100 airplane. The magnitude of structural deflections in the aft fuselage, tail, and wings of these fighter aircraft amazed the project pilots. Their comments in general indicated that the turbulence was more severe than they had ever experienced, even in thunderstorms. On one flight, the pilot took pictures from a 16mm camera mounted on his helmet. The turbulent environment can be appreciated to some extent from these shots. A preliminary analysis of the data from only 28 of these flights revealed that about 350 gusts in the range from 40 to 60 feet per second had been encountered. In the range from 60 to 120 feet per second, 80 gusts had been encountered. The shapes of these gusts varied from well-developed vortices to unidirectional discrete encounters. The rate of onset of some of the strikes exceeded 500 feet per second. Vertical, lateral, and longitudinal time histories of all flights are being plotted. The gusts will be categorized and peak counted, and power spectral analyses will be performed. It is expected the final report will be released early this fall. As we watch these concluding shots, let's reflect for a moment on where we've been, where we are now, and where we're going. It appears to me that we have reached a critical decision point. We have collected a small sample of data which underscores a major impact on the low-level tactic and threatens unacceptable losses. At this point, we cannot turn back, nor can we choose to ignore the problem. We must face it squarely and examine it in sufficient detail to give our industry designers and military operators the benefit of a complete understanding of the environment into which they are projecting our present and future machines. All too often in the past, programs have either been too hastily put together as a result of an individual crisis or have been so limited in scope as to be ineffectual. New flight test efforts should be coordinated with the many weather agencies involved to provide maximum correlation of meteo information. In addition, all test work should be geographically identified and correlated with altitude to better understand the influences of terrain. Doppler winds and temperatures should be continuously recorded to develop a sense of origin and energy levels involved with this type of turbulence. Seasonal effects should also be examined. Test planning and coordination must take place sufficiently far in advance to benefit from the talents and resources of other interested agencies. Test airplanes should not be handicapped or encumbered with extraneous and incidental tests. We should, for once, approach this problem on a scientific basis with intent to construct an analytical model of the low-level environment. The possibility of long-term cyclic trends in the severity of weather should also be investigated. Operation of our present aircraft, as well as the design and operation of future aircraft, dictate the necessity for such a program. In summary, there remains a critical and growing need for more knowledge of the low-level environment in which we are now operating.